Alright, hello and welcome back to Probabilus. If it's your first time joining us, welcome. As always, do a short introduction before we get into today's educational content. So what is Probabilus? We are an educational content creator on both Twitch and on YouTube. And we give out educational videos in a variety of subjects that will help you prepare for the AP tests as well as hopefully for the SAT. Those streams will occur a little bit more irregularly. Anyways, today is Wednesday, which means we are doing AP Calculus content. Mondays are AP Physics 1 content, and Thursdays are AP Physics C content. So that's just a brief overview of our schedule. But yeah, today is physics. If you're joining us on Twitch, feel free to put questions in the comment section, so that way we can answer them in real time. And if not, if you're on YouTube, then thanks for joining us, and hope you learn, and feel free to check us out on Twitch. But with that said, we're going to start with the first unit of calculus, which is limits and continuity. So let's jump into it. Alright, here we are, limits and continuity. I absolutely love calculus. This is one of my favorite subjects. And limits and continuity is a really good place to start because it does set the foundation for a lot of stuff that we'll learn further down the road in calculus. So, with that said, let's get into it. And we'll start with section 1, which is limits. So to begin, we'll cover the basics of limits. Essentially what the definition is, how we represent it mathematically, stuff like that. And that's all contained on this slide here. So we say the limit of a function f of x is the value of f of x as x approaches a certain number. And we see this kind of like mathematical writing there. And what we say is that expression is the limit as x approaches c of f of x equals L. And that's seen at the bottom right there. So let's analyze these symbols a little bit and really decipher what things mean. So first is LIM. That is our mathematical symbol for limit. LIM is short for limit. Should be self-explanatory. X is the variable of our function. And we see it here again, right? So we have some function that's defined, right? And x is our variable. It doesn't have to be x, could be any other variable. We could have a function in terms of y and be analyzing what happens to the variable y. Or it could just be any random function that doesn't necessarily have like a graph corresponding to it. For example, if I have like f of k equals 2k plus 1, I could very well do the limit as k approaches some number c, which we'll talk about, of f of k. That is perfectly valid. It's just the variable in question. Next is c, which I just mentioned, and that's seen right there. So that is the value that x is approaching. We say as x approaches c. So we're analyzing what the function f of x returns as x gets closer and closer to our value c. And we'll see this more in some of the examples that follow. Next is f of x, which I just talked about, so that's kind of the function we're working with. I gave an example here, 2k plus 1, so like 2x squared plus 3, something like that. That's just the function. And L is what our limit evaluates to, and we'll learn how to evaluate limits, but usually that's just a number, like 3. Or pi, or something like that. So that's analyzing what a limit looks like. But let's see if we can solve a limit. So we're given the limit as x approaches 2 of 3x squared over 2, and we want to know what does this equal. Well, what we can do is we know that f of x equals 3x squared over 2. Because that is from our definition of a limit. We had limit as x approaches c of f of x equals L, right? So we're just using this f of x part, and we're saying that f of x equals 3x squared over 2. And really what we can do is we can graph that, which is what we see on the right. So now to evaluate this, we can look at the graph, and in particular, we can look at the x variable. We're graphing an xy plane, but we're analyzing the x variable, and we want to see what does the function evaluate to as x gets closer and closer to 2. So let's zoom in a little bit here. I'll use a different color. So f of 2 is right there, that point, but let's just pretend that this is x here. And right now it's somewhere like a little bit above 3. And then we move it closer to 2 to a different place, and now it's almost 4, right? And then we move it even closer, and now it's almost 5. And then a little bit more, and we're getting closer and closer until we get ever so close to 2. And this is probably like 5.998, something like that, right? It's getting really close to 6. So it makes sense that, okay, we see here that f of 2 does indeed equal 6, because 3x squared over 2 equals 3 times 2 squared over 2, and that equals 3 times 4 over 2, and that equals 6, right? Similarly, if we were to approach 2 from the opposite side, right? If we start from here, that's x, and right now it's at like 8, and then we move it closer to 2. Here it's like 7.3 or something, and then we get closer, and now it's like 6.5, and then we're ever so close, and this is probably like 6.01 or something like that, right? So we see, as we approach it from different sides, we're still getting closer and closer to 6. So indeed, our limit evaluates to 6. And that makes sense, because f of 2 is 6, as seen on the graph. So that's how we do it graphically. Alternatively, we can find the limit numerically. And this takes advantage of the fact that we were analyzing what happens as x gets closer and closer to 1. So we can set up a table where 1 is in the middle, the value is approaching, and we can get closer to 1 from the lower side, and closer to 1 from the higher side, and see where they come together. But first, let's just see what happens when we put x equals 1 into the equation. So we have f of x equals x cubed minus 1 over x minus 1. So what does f of 1 equal? F of 1 equals 1 cubed minus 1 over 1 minus 1, which is equal to 0 over 0. We don't really know what that is. We don't know what 0 divided by 0 is, so we say this is DNE. DNE stands for does not exist. So I'm just going to put that in the table here. And yeah, we just don't know what that's equal to, because we don't know what 0 divided by 0 is. But then we can deal with some of the other values. Like let's say we put 1.001 in there. So f of 1.001 equals that value cubed minus 1, all of this over 1.001 minus 1. And if you evaluate that out, I believe you get something like 3.003. And if you do 1.01, this value here, you'll get something like 3.03, right? And then this value, 1.1, I'm not sure what it is. I guess the screen is frozen. So let me just try to fix this quickly. 1 second. Alright, welcome back, and we're going to start from where we left off, which is finding the limit numerically. So, we were on this slide, and I'm just going to restate some of the stuff that I said. And essentially, finding the limit numerically means, well, we test values of x such that we get closer to the value that we are approaching, which is, in this case, is 1. And we can do this from both sides, meaning from the lower side and from the higher side. So that's why in the chart I go from 0.75 to 0.999, very close to 1. So that's from the lower side. And then I start from 1.25 and go to 1.001, so getting very close to 1, but from the upper side. And so what happens? How do we fill out this table? Well, first we see that f of x equals x cubed minus 1 over x minus 1. So that's the value, that's the function that we're working with. And, well, we can just plug in x into f of x and see what happens. So, what happens when we do f of 1? So, f of 1 equals 1 cubed minus 1 over 1 minus 1. That equals 0 over 0. And, well, what is 0 over 0? I don't know. And neither does anyone else, really. So, for that, we just say that it's DNE, and DNE stands for does not exist. So, we don't know what f of 1 is, so we're just going to put DNE in the chart. But we can evaluate it for the other values and see what f of x approaches as x gets closer and closer to 1. So, let's just start with this like 0.9 here, right? So, f of 0.9 equals 0.9 cubed minus 1 over 0.9 minus 1. So I'm not exactly sure what that value is, but the filled-in chart is below, and we can see that it's 2.71, right? So we put 2.71 here, and then we can do 0.999, same thing, f of 0.999. That equals, well, 0.999 cubed minus 1 over 0.999 minus 1. And that evaluates to 2.997. And then we can do the same thing from the other side. This value, we plug it in, we'll get like 3.003. This one will get 3.03, something like that. So even though the function does not exist at x equals 1, we can still see as we get closer to 1 from this side, we get closer to some value. 2.997 is almost 3. When we get closer from the right side, we get 3.003, which is almost 3. So from both sides are saying that we're getting very, very close to 3. So we might as well say that the limit as x approaches 1 of f of x equals 3. Now we can see the full filled-in table here, and we can see that when we start from a really high value, relatively to the other values we're using, we get 3.812, which is like not very close to 3. But as we decrease this x value, as it gets smaller and smaller, closer and closer to 1, we see that we're getting closer and closer to 3, right? We have 3.003, right? And same thing from this side. We start at 2.313. Very, very low number comparatively. And as we increase, we're getting closer to that magic number 3. So that's how we can do it numerically. So let's just look at this term DNE does not exist a little bit more. So there's a couple of conditions in which something does not exist. And this occurs when the left limit and the right limit are not equal. So that means the limit as x approaches c plus of f of x does not equal the limit as x approaches c minus of f of x. So what are these pluses and minuses? Plus is from the right, and minus is from the left. So what does that mean? Well, if we look back at the example that we did, where we evaluated this expression numerically, we came from both sides. We came from the left towards 1, starting from the left, lower values are to the left of 1 on a number line, and that evaluated to 3. And as we came from the right, higher values are to the right on the number line. As we came from the right down to 1, that also evaluated to 3. So in this case, we had the limit as x approaches 1 minus of f of x equals the limit as x approaches 1 plus of f of x. And that equals 3. Both were pointing to the answer being 3. So in that case, the limit did exist. But if they're not equal, then the limit does not exist. Alternatively, the limit this does not exist can occur if the limit does not approach a constant number, so perhaps infinity, right? And we see that in this example here. The limit as x approaches 0 of 1 over x squared, right? If we just plugged in 0 into here, so we have f of x equals 1 over x squared, then f of 0 will get 1 over 0 squared, which is 1 over 0, and this is, well, this is actually infinity. And that's not a constant number, right? So in that case, the limit doesn't exist, or it may not exist. Keyword here is can. Just because the limit doesn't approach a constant number does not mean that the limit doesn't exist. There are some, edge cases to consider, but this is just a good signal of when the limit could not exist. Moving onwards. So now we'll really get into the properties of limits. Right now I've sort of just been, messing around a little bit, plugging numbers into functions. We've seen that, but we haven't really defined stuff. So now we'll really get into some definitions. So first, the limit as x approaches c of b equals b. And the important thing that, about this is where b is some constant. So it's not, b is not a variable, b is a constant. So if we have the limit as x approaches 2 of 4, that equals 4. And we can consider it graphically, right? If we have a plane here, right? And then what happens when we have the graph x equals 4? That's just this line, right? Well, there's not much to say, right? The limit as x approaches 2, well, there isn't much there, but it's just 4. Okay. Next, now we have a variable. The limit as x approaches c of x equals c, right? So now we have this variable that's approaching some value, and we're analyzing that as a function. And what that's saying is we can just plug in this c into x to get c. So that is a property that holds. Another thing here is if we have f of x equals x to the n for just some n, it could be 1, 2, 3, whatever, something like that, we can just plug the c in to get c to the n here. So let's just see a quick example. The limit as x approaches, let's say, 3 of x to the 7th, well, it's in this form, right? We have n equals 7, and we have c equals 3, so this equals 3 to the 7. So that's a good property for limits. So these are really important to know. They'll come in super handy. And here's some more cool limit properties. So now we have two functions, f of x and g of x, right? And we've evaluated the limit for the same point, x, towards c. And the limit of f of x is L, and the limit of g of x is k. So there's 5 properties listed here. The limit as x approaches c of b times f of x equals b times L. And here again, b is a constant. So that's just saying, essentially what this is saying here is, well, we can sort of distribute the limit. We can get limit as x approaches c of b times the limit as x approaches c of f of x. This, by our first limit property right here, that evaluates to b, and this one we're given here, that's equal to L. So we get it's equal to BL. So that's that. Second one, we can see the limit as x approaches c of f of x plus or minus g of x equals L plus or minus k. So again, something similar happens where we can sort of distribute the limit in a sense. So here we're saying that that is equivalent to the limit as x approaches c of f of x, this quantity, plus or minus the limit as x approaches c of g of x. And both of these are defined, L and k, so that's equal to L plus or minus k. So that's the second one. Third one, limit as x approaches c of f of x times g of x is L times k. And again, very similar logic here. Sort of this distribution of a limit, right? This is saying that it's equivalent to the limit as x approaches c of f of x times the limit as x approaches c of g of x. And since we're given them, again, here, L and k, this is equal to L times k. Go back to purple. And then number 4 is a very similar thing here. It's just division this time, but that's essentially saying, that's not what I want, that it's equal to the limit as x approaches c of f of x divided by the same thing, but for g of x. And we're given both of those, L over k. And they say k cannot equal 0 because, well, if we have k equals 0 in the denominator, then the limit doesn't exist, because when you divide by 0, we get d and e. And lastly, the limit as x approaches c of f of x to the n equals L to the n. So that's just saying that essentially this is equivalent to the limit as x approaches c of f of x, all of that to the n, so that's just equal to L of n. So these are just some properties that we need to know. We don't need to worry about how they're derived, but we can sort of see like some properties of how limits can sort of distribute in a way. So it's good to keep these in mind. So limits of polynomials. If p is a polynomial function, so that just means we have something like p equals 1 plus x, I guess that's not true, 1 plus like c1x plus c2x squared plus c3x cubed plus ... where c's are constants, ci is a constant, right? That's just a polynomial. And c is a real number. Well, I probably shouldn't have chose the letter c above here, but those c's are different than the c in this definition. But that's just saying the limit as x approaches c of p of x is equal to p of c. So that's just saying we can plug in c to our equation, to our function rather, and evaluate. That's all it's saying. We just plug the c into here, and we get p of c. Similarly, if r is a rational function, given by r of x equals this expression, and c is a real number, such that q of c does not equal 0, and we have that specification because we don't want this to be 0. If it is 0, then we run into issues with things not existing. Then, the limit as x approaches c of r of x equals r of c. So again, we're just plugging this into here, and that is equal to p of c divided by q of c by the definition. So that's just saying for polynomial functions and rational functions, most rational functions, if the function is one of those two, we can just plug in the value we're approaching, and that'll give us the limit. So let's see it with an example here. The limit as x approaches 2 of 4x squared minus 5. So, from our properties of limits, we know this is equal to the limit as x approaches 2 of 4x squared minus the limit as x approaches 2 of 5. And this second term should be pretty easy to evaluate, right? This just goes to 5 from the limit properties. This one is a little bit more challenging, right? So let's just put this one off to the side. So limit as x approaches 2 of 4x squared. Well, what is 4x squared? 4x squared is a polynomial. It's a polynomial function, right? It's of that form, c1x plus c2x squared, something like that, right? And what did we say about that? We said the limit as x approaches c of f of x equals f of c. So we can just plug this value of 2 into here, and that's just saying this is equal to 4 times 2 squared, and that equals 16. So this comes down to 16, and then we drop down this minus sign, right? And that is equal to 11. So that is our limit. Alternatively, you could have noticed that this is also a polynomial function. 4x squared minus 5 is a polynomial function. So we could plug 2 in, and we get, like, if f of x equals 4x squared minus 5, then for c equals 2, we have f of c equals 4 times 2 squared minus 5, which is equal to 16 minus 5 equals 11. So that's sort of a shortcut instead of breaking it apart into two limits. But I like the first way of doing it because you get to use some of the properties of limits. Here's another example. Evaluate the following. Limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. So, what is this? This is a rational function, right? And we said that, like, r of x equals p of x divided by q of x. And we wanted to make sure that the denominator didn't equal 0. So if we put 1 into the denominator, we get 1 plus 1, which is 2, which is not 0, so we're in good shape. So, what was the rule with rational functions? That said, the limit as x approaches c of, I guess I'll use r of x, that is just equal to r of c. So, let's just plug 1 into there. R of 1 equals 1 squared plus 1 plus 2, all of this over 1 plus 1. So this is equal to 4 over 2, that's equal to 2. And that's our answer. So that's good. So now we'll do a little bit more definitions and stuff. So the limits of functions with radicals. So we're letting n be a positive integer, and the limit below is valid for all c when n is odd, and is valid for c is greater than 0 when n is even. So we're saying the limit as x approaches c of the nth root of x equals the nth root of c. So we really want to just say that, oh, I want to plug in the c into the function, and that's what the limit is. However, it doesn't completely work because the roots work differently when n is even or odd, right? If we have the cube root of negative 125, right, this is equal to negative 5, and we have, like, a negative value that's allowed. But if we were to take just the square root of 64, we say that this is only equal to 8. We're taking the principal square root of it. So it's just a little bit of how the roots are defined, but essentially it's just saying we can just plug in the c. Next is limits of composite functions. So if f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches L, which is the result of the limit of g of x, if that limit is f of L, so that's just saying plug the L into f, then this expression, the limit of f of g of x as x approaches c, equals f of L. So how exactly does that work? Well, that's sort of taking this limit and squeezing it in between and saying we're evaluating f of this limit, right? And this limit is given to us, which is to be L, so thus we're computing f of L. That's sort of how the theory works. So now we have some trig functions and the limits of them. So c is just a real number in the domain of the trigonometric function. And, I mean, essentially you can read them here, but it's just saying that the limit as x approaches c of that function is that function evaluated at c. So that's pretty simple. You know, we just have to make sure c is in the domain of that function. But yeah, otherwise, you just plug it in. So let's evaluate the following. The limit as x approaches pi of x times cosine of x. So we should remember from our limit properties that this is equal to the limit as x approaches pi of x times the limit as x approaches pi of cosine of x, right? And this one we know that x is like a polynomial function, or even the one limit property said that the limit as x approaches c of x is just c. So this evaluates to pi. And then we're multiplying that with this limit, right? And we just saw that the limit as x approaches c of cosine of x is cosine of c. So this evaluates to cosine of pi. So we can simplify this further, which comes down to pi times what's cosine of pi. That's equal to -1. So our answer is -pi. Right? So that's that. So here we have a little interesting video. So let me just pull it up. And we can see what happens graphically. So I'll play the video, but what we see is in pink is the graph x times cosine of x. And we have some point, which is right now starting at, I believe, -pi. And it's going to move towards the right until it reaches x equals pi. And the number that's shown right now, 3.142, is the value of the function at that value. So let's just play it and see what happens. So we can see that it stopped at pi, and I'll play it again, right? It stopped at x equals pi, but it evaluated to -3.142, which is -pi. And that's exactly what we got when we solved the expression, right? If we go back to what we just solved, we see that we got -pi. So that was just a graphical view of what was going on. So what happens if we're dealing with a function that's missing a point? And that can happen. We can have a function where there's no value at that point. So let c be a real number, and let f of x equals g of x for all x not equal to c in an open interval containing c. Okay, so we have some sort of interval, right, from here to here, and we have f of x equals g of x, so it's the same function, except for some point c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists. And we have this relationship right here. And that should sort of make sense, right? They're essentially the same function, except at the one point, but their limits are equal to each other, right? Because they are equal limits from both sides. And to see this better, we'll see it in an example, but we can evaluate such functions by factoring, canceling, etc. So let's see an example. So evaluate the following limit. The limit as x approaches 1 of x cubed minus 1 over x minus 1. So this is actually the second example that we did with the table. It's the same exact function. And we see that it's graphed here, but at x equals 1, it's undefined. The function is undefined. So this is a function where it's defined everywhere except at one point. It has a hole, right? So how can we solve this, right? Well, if we try our usual method of just plugging in x equals 1, what do we get? We should run into problems, and we do. 1 cubed minus 1 over 1 minus 1 equals 0 divided by 0, and that's dne, right? We did that example previously. So what can we do to solve this? Well, we can do some factoring. What do we know about x cubed minus 1? This can be factored into x minus 1 times x squared plus x plus 1. And if you don't believe me, we can, multiply it out. And since I don't really trust myself, let's just do it just to be sure. So we'll multiply the first terms, we get x cubed. This times that is x squared. This times this is plus x. This is negative x squared. This is negative x. This is negative 1. These two terms cancel. These two terms cancel. And that's left with x cubed minus 1. So we factored it. So that means we can rewrite the original limit as the factored version. So we have x minus 1 times x squared plus x plus 1 on the numerator, and x minus 1 on the denominator. And I suppose that I should have included the limit symbol, because that is very important. We haven't finished evaluating it. And now these cancel, and now we're just left with the limit as x approaches 1 of x squared plus x plus 1. This is a polynomial function, polynomial. So we can just plug in x equals 1, and we get 1 squared plus 1 plus 1 is equal to 3. And that's the value we got earlier when we did it with the table, right? And that's the value we expect to get, because as we get closer to here, this is y equals 3. And same thing, as we get closer from the right-hand side, we get closer to y equals 3, f of x equals 3. So we can use factoring to our advantage. Now we have this example. Limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. And this one seems tricky. But limits aren't tricky when we can just directly substitute. So let's see what happens when we directly substitute. Let me just keep it clear. Substitute, right? So the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Well, we're saying this is equal to the square root of 0 plus 1 minus 1 all over 0. And we can see we're going to run into errors very quickly because of the denominator. But if we simplify this further, we get 0 over 0, which does not exist. And it is very possible for limits to not exist. That is an acceptable answer to a limit. But we have to do some other things to make sure that we are certain that the limit does not exist. And for this one, there are things we can do. So we just learned about factoring, right? And I mean, looking at this expression, it seems quite difficult to factor, right? We're dealing with a radical, which isn't fun. So something we can do, especially with radicals, is multiply by the conjugate. And in fact, we're going to multiply it by a form of 1 implementing the conjugate. So we can say that the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x is equal to this same limit, x squared plus 1 minus 1 all over x, times, and we're going to construct a fraction here. And we want this fraction to be 1, so we want the numerator and denominator to be the same. So we're going to multiply by the conjugate of the numerator, since that has the the radical in it. So the conjugate is essentially the same exact thing, same terms, except we change the sign. And we can see that this new term in parentheses is a form of 1. The numerator and denominator are same, so it equals 1, and that's the same limit. We're just multiplying by 1. So if we evaluate this out, let's see what happens when we multiply it. So we get x plus 1 minus 1 times x plus 1 plus 1, that all over x times x plus 1 plus 1, right? And if we, do some wonderful arithmetic, we can see that this top term, this will just evaluate to x plus 1 minus 1, and the denominator will stay x plus 1 square root plus x. The numerator simplifies a little bit to become just x, and the denominator stays x plus 1 plus x. So now we have a rational function, right? It's a fraction type thing, and we want to make sure that the denominator is not 0. So, let me just make sure I did this correctly. X plus 1, yeah, okay. So, the denominator right now would be 0 times the square root of 1 plus 0, which is still equal to 0. So we would still have 0 divided by 0. But there's still something we can do to simplify this a little bit. I'm just going to move it over here. What we can do is actually, we can go back to this form for the denominator, where we didn't multiply it out. And let's see what happens. So if we factor out an x, we can see that the x's now cancel. And we're left with the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. So even though, we had this somewhat simplified form, this gave us 0 divided by 0. But with just a simple fix, we now have it in this different form, and we can see it's not going to equal 0 over 0 because the numerator is not 0. And now, if we check the denominator, does that equal 0? Well, 0 plus 1 is 1, square root of 1 is 1, 1 plus 1 is 2. So we're good, and we can directly substitute, and that's exactly what we'll do. It's the same computation I just said, but I'll write it out now. And that's equal to 1 over 1 plus 1, which is equal to 1/2. And that's our answer. So this was a tricky one, right? It seemed difficult from the start, and it was difficult. So we learned a couple techniques. First, we learned above factoring. Now we learned multiplying by the conjugate. And multiplying by the conjugate works when we have square roots being added and subtracted with other real numbers. So now we'll learn the squeeze theorem, which very strange theorem at first glance, and when you first learn it. However, it's extremely important. Later on down the road, it can help you learn a lot of topics. Not even just in math, but even in computer science, there are some applications of this theorem. And we can really stretch it to understand other theorems that are important. So this says, if we have three functions, h of x, which is less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself, and if the limit as x approaches c of h of x is L, which is the same as the limit of g of x, then the limit of f of x exists and is equal to L. So what does that mean? There's a very good picture here. And I'm just going to rewrite the inequality that we started out with, because this is very important. So this is saying f of x is greater than or equal to h of x for basically all values of x. So h of x is a lower bound for f of x. And similarly, g of x is an upper bound. And it's for a very similar reason, right? Essentially it's h and f, but the roles are flip-flopped. Right now, f of x is the lower bound for g of x. So f of x is in between these two functions at all times. And now we're saying, if the limit at some point c of h of x equals the limit as x approaches c of g of x, then f of x has to have a limit there, and that limit is equivalent to the other two. Why? Because it's upper bounded and lower bounded by these two functions, so it has to be in between these two functions, and if they're at the same point, g and h are at the same point, because that's why the limit is equal, then f must also be at that point. And the reason it's called the squeeze theorem is because f is squeezed in between g and h. It's squeezing through this little tiny space here, which is technically no space at all, because g and h both have the limit evaluated at the same value at that place, so f has to be in there. It really helps to think of it as a lower bound and upper bound. So this is a very important theorem. Alright, let's do another example. So we have the limit as x approaches 2 of that equation. I'm not going to read it. So let's try our favorite trick, direct substitution. And remember, if direct substitution seems to work, then it's probably right. So we can just plug in x equals 2, and we get this sort of thing, right? 2 squared minus 2 minus 2. So this is equal to 4 plus 4 minus 8 all over 4 minus 2 minus 2, which is equal to 0 over 0. So this is no good. We don't like seeing that. So now we can try something else. Conjugate doesn't make sense since we're not dealing with the square root, but factoring makes sense, right? Because we're doing polynomials. So x squared plus 2x minus 8, that is equal to x plus 4 times x minus 2. That's just simple factoring. Similarly, x squared minus x minus 2 is equal to x minus 2 times x plus 1. So what we can do is we can rewrite this limit. I don't feel like writing it, so I'm just copying and pasting it. But this is equal to the limit as x approaches 2 of this factored form. And what we're going to see right now is that they share a term in common. X minus 2 is common in between them. So we cancel them. And this simplifies a little bit more. X plus 4 divided by x plus 1. And if we do direct substitution, we see that this equals 2 plus 4 divided by 2 plus 1 equals 6 divided by 3 equals 2. And that's our answer. So that was pretty nice. We used factoring and direct substitution to help us out there at the end. So that was a good question. So now this one. Use the squeeze theorem to evaluate the limit as x approaches c of f of x. And we're given c equals 0, and f of x is sandwiched or squeezed in between these two functions. So from the definition of the squeeze theorem, we had this inequality, right? So let's just say that this is h of x, and this is g of x. So the squeeze theorem tells us if the limit as x approaches c of h of x equals the limit as x approaches c of g of x, and that's equal to some value L, then the limit as x approaches c of f of x equals L. And this is what we're trying to find. So let's check if this is true. So the limit as x approaches c, and c is 0, of h of x, which is 4 minus x squared, well, we can do direct substitution, and we have 4 minus 0 squared, and that's just equal to 4. So that's pretty good. And now we'll try g of x, the limit as x approaches 0 of 4 plus x squared. Similar thing here. That gives us 4. So this is true. So that tells us that the limit as x approaches c of f of x equals L, which is equal to 4. So that's using the squeeze theorem. Nice. So now we'll move on to section 2, which is continuity. This section's a little bit shorter. So first we look at the conditions for discontinuity. We can have continuity and discontinuity. So by definition, if none of the following conditions are true, then a function f is continuous at c. So we're defining continuous based off of the non-existence of certain conditions of the function. So number 1, if the function is not defined at x equals c, then it's not continuous at c. So that's seen in this first picture here, right? There's no value at x equals c, so it's not continuous at c. In this case, there's a hole, so we call this a hole. 2, the limit of f of x does not exist at x equals c, and that's seen in the second picture here, right? If we approach c from the left, we're getting to some value around here, but if we approach c from the right, we're getting to a completely different value, so the limit doesn't exist, because the limit from the right does not equal the limit from the left. Or 3, the limit of f of x exists at x equals c, but it is not equal to f of c. So this is seen here, and this is where we have a hole but c is defined elsewhere. So the limit we can see from the left, it's approaching some value here, and from the right, same thing, but that limit does not equal this point down here. So it's not continuous. There's a hole, but it's just defined at a different place, the function. So if a function is any of these three things, then it's discontinuous. If it's none of these three things, then it's continuous. So assessing continuity. So to assess continuity, it's helpful to use the one-sided limits. So we've been talking about this quite a bit today, but here it's defined a little bit better. And by this we mean we should take the limit from the right and the limit from the left of a specific point that we're testing for continuity at. So if we're trying to see is f of x continuous at a certain point, we would want to evaluate the right and left limits of that function at that point. And that's seen here. Again, we have the notation c plus c minus. Next is the limit existence theorem. So let f be a function, let c and l be real numbers. The limit of f of x as x approaches c is L if and only if the limit from the left equals L and the limit from the right equals L. So this is something we've alluded to previously today, but that's just saying if we have some graph here, that's just a plane, and we have some function, and we're assessing it at this point C here, we want, that's not a good color. We want the limit as we're coming from the left-hand side, which is some point here, to be the same as when we approach it from the other side, which in this case it is. So that means the limit exists. Now we have continuity on a closed interval. So function f is continuous on the closed interval, a to b, when f is continuous on the open interval, a to b, and the limit as x approaches a from the right of f of x equals f of a, and for b from the left equals f of b. So here we say that it's continuous from the right at a and continuous from the left at b. So let's just define these things. When we have closed brackets a and b, it's like all points from a to b, including a and b. And this, when it's parentheses, is just all points. Actually, let me just copy and paste it. It's all points from a to b, excluding a and b. And let's just change this to make sure it's correct. So it's essentially the same thing, just two points are included in one and not in the other. Now we have the intermediate value theorem. This one's quite important too. There's always multiple choice questions on the AP exam about the intermediate value theorem. So we have f is continuous on the closed interval, a comma b, and f of a does not equal f of b. So we have some endpoints of an interval, and their function values are not equal at those values. K is any number between f of a and f of b. So these are the function evaluated values of the endpoints. Then there's at least one number c in AB such that f of c equals k. So this is really saying a is less than or equal to c, less than or equal to b. So it helps to see this picture here. So we have a function right now, f, which is continuous, and this is a, this is b, right? Then there's some point in between, which we'll just call c2, such that the limit, or rather the function evaluated at that point, is k. And we notice here that this is the function evaluated point at one endpoint, and this is the function evaluated point at the other point. So k can be anywhere in this range. But the point is, no matter what k we choose in that range, there will always be some point in the function where it's evaluated to k. So let's say we let k equal like down here, right? We can see, right here, there's some point which we'll call C4, where f of C4 equals k. So that's a pretty cool theorem. And here we have a discontinuous function. It's non-continuous on the closed interval, which means that there probably is some k where it's not, evaluated. Function's not evaluated. And we see that right here, where k is like in between this jump between the two parts of the function. And it's called the intermediate value theorem because this k is intermediate. It's in between a and b. Cool. So use the intermediate value theorem, and sometimes this is abbreviated as IVT, to show that f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0, 1. Alright, so this one seems a little bit difficult. And if we weren't given that we should use the intermediate value theorem, it may be a little difficult to prove this. But we have that, okay, f of x is just some function which it doesn't really matter what it looks like, but the point is we know that it's continuous on the interval 0, 1 because, well, we can just tell there's no point in which there would be a discontinuity. You can't really think of any point where it would be discontinuous. It's hard to think of something. So we have this interval here. So let me change colors. So this is 0, and let's just say this is 1. So those are our endpoints. We have like a equals 0 and b equals 1. Okay? So let's go back to the intermediate value theorem. And let's check, does f of a not equal f of b? F of a equals f of 0, which is equal to 0 cubed plus 2 times 0 minus 1, which is equal to negative 1. Similarly, f of b equals f of 1, which is equal to 1 cubed plus 2 times 1 minus 1, and that's equal to, well, 2. So we have f of a does not equal f of b, which is good. That is a good start for the intermediate value theorem. So what does this tell us? K is any number in between f of a and f of b. And we're looking for if the function has a 0 in the interval. So let's just let k equal to 0. Because after all, we want f of like some value, which I'll say c, to be equal to 0. If this is true, if true, then we have a 0. Just by the definition of what a 0 is. And this is where a is less than or equal to c less than or equal to b. So, now we'll just say that k equals 0, right? So, literally we can just say that by the IVT, there must be some c, there must be such that, well, first we should put some constraints on c. So 0 is less than or equal to c less than or equal to 1, right? It has to be in that range, such that that is true, and f of c equals k, which is equal to 0, right? It's a very similar thing to here, right? Where we had f of a, in this case it was negative 1 and 2, so let's just set this one to be negative 1 and this one to be 2, right? And it's continuous, so there's a k right here, and this can equal 0 because it's in between these two values. So there must be some point on the function where evaluated at that point it's 0. So that's a good use of the IVT. So now let's talk a little bit about infinite limits. So an infinite limit is a limit such that f of x increases or decreases without bounds, that's the term we use, as x approaches c. So these limits, as the name suggests, evaluate to positive or negative infinity, plus or minus infinity. So if the limit as x approaches c of f of x approaches positive or negative infinity from the right or left, then the vertical line x equals c is a vertical asymptote. Okay, so now we have a little bit more at the bottom here. We have two continuous functions on an open interval containing c, and one function at c is 0, the other one's not 0. So then there exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval. So if we have those two things, then the graph of this function has a vertical asymptote at x equals c. And the main thing about this here is that g of c equals 0, right? So that would put a 0 in the denominator, 0 in denominator, when x equals c. We don't have to really worry about when x is not equal to c, because we have g of x is not equal to 0 for all x not equal to c. But when this is true, we have a 0 in the denominator, and this is a sign of a vertical asymptote. And I'll abbreviate some words just to save time. But yeah, generally, if we see that the denominator equals 0 at some value, then there is a chance that that value has a vertical asymptote. It's not guaranteed, but it's possible. So to see that, we want to find all vertical asymptotes of the graph that, f of x equals that. So first, let's just see what values make the denominator equal to 0. Well, let's just let's just set the denominator equal to 0. And we can see that, okay, x squared equals 4, which tells us x equals plus or minus 2. So these are essentially the only places where vertical asymptotes are possible. So vertical asymptote can only occur at x equals plus or minus 2. But now we have to make sure that certainly there exists a vertical asymptote there. Right now it's not guaranteed, we've just determined the places where it could exist. And to do this, well, we can notice that f of x can be factored. So f of x actually equals, well, right now let's just rewrite it. But the denominator is the difference of two squares, and we should remember that that is equal to the summation of the squares times the difference of them. And the top part, well, that's equal to x plus 4 times x minus 2. And we see that there's a cancellation that occurs. So we have f of x equals x plus 4 divided by x plus 2. So now we see that at x equals 2, f of x equals 2 plus 4 over 2 plus 2, which is equal to 6 over 4 equals 3 halves. So in actuality, I'm just going to rewrite this, 2 or negative 2. There is no vertical asymptote at x equals 2, because now we've seen that it has a value. It's equal to 3 halves. F of x equals 3 halves at x equals 2. That's just what it is. Now we can check for negative 2. So at x equals negative 2, f of x equals negative 2 plus 4 over negative 2 plus 2. That equals 2 over 0, and that means we have a vertical asymptote, because there's nothing more we can do to simplify it. So only one asymptote, well, only one vertical asymptote at x equals negative 2. So that's our solution. Good. So we do need to be careful. Even though that there might be multiple values such that the original expression has a 0 in its denominator, we have to be careful that we can't simplify it. And when we do simplify it, we need to make sure we're simplifying all the way. Alright, a couple more slides and then we'll be done for today. But first, properties of infinite limits. So we have C and L are real numbers, f-integer functions. The limit of f of x is infinity at C, and for g of x it's L, which is a real number. So the sum, well, this, if we remember our properties of limits, this is just the limit as x approaches C of f of x. That plus or minus limit as x approaches C g of x. And that's equal to, well, this evaluates to infinity plus or minus L, and it doesn't really matter what L is because infinity is infinity, so it's just going to be infinity. Same thing here, similar logic, but we'll just get infinity times L, and that just means it's equal to infinity. That's just how infinity works. And then same thing here, it's a negative infinity when L is less than 0, so it's just a very similar thing. Negative L, the negative actually does play a part, it does flip the sign of infinity, so that's just another property of infinity. And if we take the quotient of them, well, this would be something like L divided by infinity, and infinity is a really big, really big. So it doesn't really matter what L is, because we're dividing by such a huge number. Like if L is 2 to the 100, infinity is infinity. So if you divide 2 to the 100 by, let's just say 2 to like the 1 million, which isn't even close to infinity, I guess that's 10 million, you'll see that this nears down to 0, it approaches 0. So when infinity is really, really big, it doesn't matter what the numerator is, it's going to be 0. Alright, we have another evaluation question. I think just 2 more problems, and then we'll call it a night. So this one's pretty simple. We have the limit as x approaches 0 from, not the right, from the left of 1 plus 1 over x. So, direct substitution, first thing to try. We get 1 plus 1 over 0, and 1 over 0 is, I don't know. That's just, I just don't know what it is. But the hint we're given is that we're approaching 0 from the left. So if we look at a set of axes here, this is 0. What would be approaching from the left? We would be coming this way, right? And if we remember the table method that we did, we were evaluating at 1, and when we came from the left, the last value we tried was 0.999, so we were very close to 0. So if we were to do the table method, the number we would try right before 0 would be a very small negative number. Let's just say, for the sake of this, it's 0.0000000000001. That. Now let's try to evaluate the limit. So the limit as x approaches 0.0 of 1 plus 1 over x equals 1 plus 1 over, and I'm gonna do some technology here, 1 plus this. Well, what is this? This is, well, a huge number. It's huge. And you can evaluate this yourself, right? We can represent the bottom part in scientific notation. Let me just change colors, right? This goes to like 1 plus 1 divided by, this is 1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 11. That's just equal to 1 plus 10 to the 11, which is huge, right? But this isn't even the smallest number we can get. We can get even smaller and closer to 0. But no matter what we get, it's going to be a huge number. However, something I've completely forgot about is that the number has to be negative. So we need a negative sign here. So I'll throw that in. And this would be a huge negative number. Well, what's a huge negative number? Negative infinity. But we also have to carry down this 1. So we get 1 plus negative infinity that's just equal to negative infinity. And that's that. And now we move on to the last question of the day, which has 3 parts, unfortunately, but these are pretty simple. So we have 2 graphs of f and g, which are functions, and we just want to evaluate each limit. So A, we'll just use some limit properties that we've learned today. F of x plus 4. This is equal to, using the properties, limit of f of x plus the limit of 4. This is 4, because that's a property. And this, well, we just look at the graph, and we see as we come from the left, we approach 2, and as we come from the right, we approach 2, right? That's this point here, but I don't want to color it in. So this is 2, and then we just sum these together to get 6. Right? So that's part A. Part B. The limit as x approaches 3, 5 divided by g of x. This is equal to, by the properties that we've learned, that divided by the limit for g of x. And the top should be pretty easy to evaluate. And the bottom, we look at the graph, and we don't have anything from the right side, but from the left, we see it's approaching, this is 1, and it's evaluated at 1 there. G of 3 is 1. So we put a 1, and the answer is 5. And last question of the night, limit as x approaches 2 of f of x times g of x. That's equal to limit as x approaches 2 of f of x times limit as x approaches 2 of g of x. And this, well, we look at the graph, and as we approach 2, oops, that's on the eraser. As we approach 2 from the left, we see that it's getting close to f of x equals 2, and from the right, same thing. So this evaluates 2, and for g of x, if we approach from the left, we get closer to 0, and from the right, same thing, 0. So this is equal to 0. And that concludes today's lesson. So, just a brief recap of what we did today. We talked about limits and continuity. These are super important terms in calculus and things you should be really familiar with, because a lot of stuff we do down the road depends on a solid foundation of these topics. And today's lesson was kind of long because we got through an entire chapter in one video. In the future, we do have, multiple chapters in calculus, but we'll try to break it up into separate videos, separate streams, just so it doesn't take super long and we can sort of stay on pace with what you've been learning in school. So that'll do it for today. That's the first lesson. Congratulations. Next week, we'll start with the next chapter, which I'm really, really looking forward to. And yeah, so hopefully you enjoyed this video. Today is Wednesday, the 15th of September. Tomorrow is Thursday, the 16th. And on Thursdays, we do AP Physics C. So if you're taking that class, please feel free to tune into the Twitch stream, which occurs every Thursday. And Monday, we'll be back to Physics 1. And next week, on Wednesday, I will see you here for calculus. With that said, that's going to do it for today. Hope you learned something, and have a good night. Bye-bye.